Hi everybody and welcome back. Well, we're going to start this video off a little bit different than we normally do. We're going to start this video in the middle of a repair. And the reason is part one of this video has been lost. Yes, you heard it. I had two bad things happen. Number one, I was trying a new microphone and the sound was absolutely horrific on it. It was terrible. It was one of those, I got a good price on it. It was too good to be true, and it was too good to be true. So I tried it out. It didn't work. I'm getting rid of it. And I went back to my wired microphone, so I'm still tethered to my bench. Here it is. But honestly, the sound quality on this thing, I've really been happy with. So I'm going to stick with it. Second of all, several of the clips got lost. When I came down and put the card in to shoot the next series of clips, it formatted incorrectly and I lost some clips. So that whole video was pretty much a bust. So what I'm going to do is I'm going to spend the first part of this video. I have lots of pictures and everything from this project. So I'll kind of get you caught up to where we are. I'll show you what we did. And I'm going to show you a couple of unique things that I'm going to have to do on this receiver because of a couple of problems that it had that we're going to try in this video to repair. So the first part of this video, those of you who just want to see getting the meter out and troubleshooting and repairing something, you're going to be disappointed, so skip ahead. Go ahead to the middle of the video where I actually am going to do some work on the receiver. This first part, we're going to go over what I did. And we're also going to go over a couple of concepts. One of the problems, well, we'll get into it. I'll show you on the bench. And after we do that, then we'll pick up where we left off and get back to the actual repair. Okay, first of all, here is the G7500. You can see the front of it. It's called a pure power DC stereo receiver. We're going to get a little bit into what the DC means. It doesn't mean direct current, believe it or not. Many of you probably already know that. When this receiver came in, one of my cousins actually got this, and I think he got a really good deal on it, and one of the channels was out on it. And he said that he saw burned components inside there, and that was a little bit of an understatement. I'll show you here. I do have some photographs of the board, how it showed up. And we'll get into that. I'll kind of post them up on the screen as we're talking here and let you take a look at the before. And what I did prior to this video is I went through and I cleaned off all those parts. I cleaned all the soot and the burn marks and everything off the circuit board. I replaced, pretty much did a wholesale rebuild of the board. And if we look down here, here are the components that were replaced. So these four transistors here were dead shorted. And something very unique is these output transistors that were used. This is a 90 watt per channel stereo receiver. It's actually a very good, well-known receiver. But a couple of the things to take note about these, this era of Sansui receiver, from the early 80s, I believe this is late 70s, early 80s. I think 79, 81, 82, something like that. These boards are kind of like those Harman Kardon ones that we worked on prior, like the PM665 and 655, whereas the tracks on these boards are very delicate, and they will burn up or break or crack or snap off very easily. This is the repaired board. It was a big mess when I got it. Again, I'll show you some pictures that I have of it. And you can see, from a distance it looks really good, but when you get up really close, you can see how much repair work I had to do, like down in here. I actually had to take a piece of copper foil and make an actual trace for this whole trace across here is missing. It was broken. And I had to kind of make a little splint, if you will, and replace that. And all of these little pads were broken off here. You can see all of these along here, this one down here. Several of them up in here were broken. couple of them up here were broken. You can see the one on the differential input pair, which is a JFET pair. You can see one's broken there. Some of the corners of some of these were broken, and some of them were burned. A lot of them were cooked along in here. I replaced all these wires. And this is a kind of a modified, basically when Sansui built this, they took an existing parts and they modified them to make this new receiver. We'll get into that in a minute also. So you can see right here we have the old output transistor boards, and those are what held these output transistors. There were two outputs on each channel, you know, PNP and NPN. And here's the boards, and you can see kind of how cooked up they are. And the wires were melted and just generally not in very good condition. So I replaced all that and rebuilt the board. Now here's the strange thing. These output transistors were mounted to these boards. And let me back you out a little bit. Okay, so they were mounted like this. So if you put the transistor in this way, and they were mounted in here like so, and this hole lined up this way, kind of like a sandwich. And then they had this heat sink, which is a two-piece heat sink. And so you have a two-piece heat sink here, this is the rear of the heat sink. So this would face the inside of the receiver. This side was facing the outside of the receiver. And then this other piece attaches to it like this, and it thermally couples to it like that with screws. And all the screws were stripped out and things. And I still need to clean this. I cleaned this one already. But you can see very clearly that this is designed for a TO3 type transistor. I'll show you what they look like here. So here's a TO3 transistor. This is called a TO3P type case. And believe it or not, if you bend these leads, first of all, the center lead is connected to the collector. And it's also connected to the heat spreader. So this is the collector, and this is the collector. On a TO3, this is the collector. So if you look at it, the pins actually line up with the pins on the TO3. See how they're lined up together? So what you can actually do is I could bend these leads downward like this. I don't care. This is the shorted out transistor, so I'm not trying to be nice with it or anything or worry about it. But these are designed to take the place of a TO3 case. So you can move this out of the way, and this will plug, well, this way. This will plug right in and fit right in place of the regular TO3. That's at least how they're supposed to work, okay? Now in this little thing, it's a little bit tight. We'd have to clip the corner off here so it would fit, but it'll even plug into sockets. So it's a direct replacement, believe it or not. But this is the correct component for this heatsink, and you can see they go right in there like that. So once again, the way they did it doesn't make a lot of sense to me. They flipped this, the original design for this heatsink. This came out of I'm sure they used this heatsink on an older model of Sansui. Any of you Sansui guys probably would know. And they had these TO3s in there like this. And they were mounted from the front like this. And then this went over top of it, and see these cavities in there that would make room for the tops of these so they don't touch. See? And that would go on there. But instead, from the inside, they mounted these transistors right here to the board like this. And they made this little adapter board for this amplifier, and then they just stuck it right on the rear of the heatsink, right on top of the paint and the anodized finish and everything. There isn't even any, and you can see this hole down here. Not very good thermal coupling the way they did it. They had this one here, and then they had the other channels over here like that. And that's how it was wired. Very strange, when really there should be, these two holes were originally designed to accommodate a socket like this one. So you can see you have the two mounting holes on the flanges there that should line up with this, and then this goes in here, and then the transistor plugged in from the front. That's how it should be. Now, why did they do that? Okay, this is why we're taking some time at the beginning of this video to go over all this. I want to catch you all up with this. The reason they did that is these transistors are different than a standard audio output transistor. These are called LAPT, all right, transistors. And LAPT, I'll show you here, stands for linear amplifier power transistor. And the big difference between these and the old style, like this MJ21194, is the transition frequency. You can see these ones are good for about 70 megahertz, whereas these ones are only good for about 4 megahertz. Now, you might say to yourself, well, what the heck does any of that even matter? I mean, audio is 20 kilohertz. That's the highest your ear can hear. I mean, you know, let's say you can hear up to 30 kilohertz. That's still a far cry from 4 megahertz, let alone 70 megahertz. Well, at the time these amps were being built, they were really talking about something called TIM distortion, or transient intermodulation distortion. And I'm not going to really get into what it means, and I'm not going to get into its relevance or irrelevance. But all I'm going to say is that that was a big thing at the time of these amps, and these fast, quote unquote, fast transistors were being used. One of the advantages of them was actually because of the use of feedback in the circuit. They were a lot faster response with feedback. And again, you have to get into a lot of theory to get into that, but you know why that's significant. But supposedly it makes a difference in the sound quality, especially at high frequency responses. Okay, it's all debatable, and again, it is what it is. But one of the other things, one of the disadvantages of them is because they had such high frequency response, it means that they were very prone to high frequency oscillation, up in the tens of megahertz. And those oscillations would actually just short out the amp, and it would just melt down. And what do I mean by meltdown? Well, take a look. You tell me what you think. So here's some of the components. Other than the 4 transistors that were dead shorted that I found, look at some of these resistors, how burned up. They're open, of course. But, you know, like these were burned right. Some of them were burned so bad off the board, all that was left was the leads. And part of it, I think, was because one of these bias pots was open. It reads open. And I'm sure that has something, but not everything, to do with it. This little bias stabistor, we'll get into what this does a little bit later, but the leads were broken off of it and had been tack soldered back on very loosely. And I think when they broke off, I don't know, because I don't know the history of this amp, that would probably cause a problem also with your bias. It would probably make the bias go way down. You know, the amp wouldn't work properly. But lots of problems. The relay had been worked on. You could see it was kind of pried apart, and the contacts were really janky, so I had to replace the relay for the speaker protect. Lots of things just needed fixed. So we got it all done, And as you can see, it turned out, you know, at least to me, it turned out pretty good, I think. I'll show you the front here. Let me turn it around. So here's the front that's all rebuilt. Hopefully I have a picture of it before it was rebuilt. But it looks pretty good. Came out good. And so here's where we are now. If you look at the schematic, let me grab a schematic. And I wrote a few, let's see here. I'm going to get it a little better angle for you. So look at the top here. And here's a couple of the substitutes I used for these transistors. So wherever you see these numbers here, I used these numbers here. And this one over here, I used for the 2SC2071, I used a KSC3503. And for its complement, the 2SA939, I used a KSA1381. The rest of them you can read for yourself. And then for that stabistor, which I showed you here that's broken, we're going to have to make something. And we used a little device called a CMX STB400. And I'll show you the, let's look at the diagram for that. Actually, I don't have it on the bench, but we'll get into a little some detail about this before we go to finish the rebuild. Now what I'm going to try to do is we're going to do a little experiment with this amplifier. These transistors are made by Sanken, okay? You may have noticed that when I showed you the front data sheet for it. And Sanken is known for these linear amplifier power transistors. And it also stands for large area parallel transistor. I've heard that term used as well. Because the way these are built is they're built as a bunch of small... So for instance, this little transistor can't handle near the amount of power that these big ones can. But its advantage is that it has a very, very high frequency response, or a high transition frequency. What is transition frequency? Transition frequency is the frequency at which the gain, or the HFE of the transistor, becomes unity, or where there is no longer any forward current gain of the transistor. And when you get above that frequency, as you get higher above the transition frequency, it actually begins to attenuate the signal as you go higher in frequency. So these ones, again, have a very high transition frequency, and so does this little one. Now, how did they do that? Making a large, high-powered transistor high frequency is extremely difficult. So the way they do it is, in this technology, is they take a whole bunch of little tiny transistors with very high frequency, and they put them all on the die in parallel. So think of this one transistor as a whole bunch of little tiny transistors all in parallel that can handle the amount of current that a power transistor would need to handle. And that's what you have in an LAPT transistor. Now, the competitor to this would be the ring emitter transistor. Okay? And ring emitter transistors are a different technology how they make them, but they basically do the same thing. The ring emitter is almost like a think of it as a big parallel circuit to allow a very high transition frequency while still being able to handle high current. So, same idea. Pioneer uses the ring emitters, and like Carver uses these, I think, in some of their amps. Sansui uses these, and I think Kenwood they also used ring emitters. I might be wrong, though. Correct me if any of you know. But anyway, the thing you just need to take away from this is these are high frequency, They give you that minimizing the Tim distortion, okay, and giving you the better feedback response and so forth. But they're also very, very prone to oscillation. It's called parasitic oscillation. And I think that's part of the reason that these fail like they do. So what we're going to do, what I'm going to try, is I'm going to remove these, and I'm going to convert this back to the old style. Any of you that have ever seen the Sansui 9090, for instance, or the 9090 dB, the 9090 uses a quasi-complementary output. The 9090 dB uses a true complementary, meaning one NPN and one PNP, whereas the quasi-complementary uses two NPNs on the output. Anyway, we're going to try to replace these with these. Why? Well, two reasons. Number one, these will properly fit on here, and they will properly thermally couple to the heatsink. These are 100 watt devices. These are 250 watt devices. So they can take a lot more torture before they'll short out. These only have a transition frequency of 4 megahertz. These have a transition frequency of 70 megahertz. You may say, well, my high frequency response is going to sound horrible because of what you just said earlier. Well, keep in mind, the Sansui 9090 and the 9090 dB and the 8080 and the 5050 and that whole series, they all use this type of transistor. The Pioneer SX750, SX850, 950, 1050, 1250, they all use this transistor. The 980, the 1080, the 1280, the 1980, they use the ring emitter transistors. If you took a Pioneer SX980 and an SX950 and you listened to them side by side, I don't know. You tell me how much better one sounds than the other. It's always a source of debate. Some people say no difference, some people say big difference, some like the 950, some like the 980. Very subjective. But I'm going to argue that if we put these in there, it's going to work. The only thing is we may have to fiddle around with the bias a little bit. And that's where this little fella comes in. Okay, what is that? This is called a stabistor, or sometimes they call it a varistor. Well, not really. Or a thermistor, which some of those terms are not correct for what this really is. But what their main job is they are used in the bias circuit of an amplifier. So if you look on the heatsink, this little dotted line here represents the heatsink, and there's your two transistors, the two outputs. And attached to that same heatsink is this little device called the STV3H. And that's what this little thing is. It's just a little device with two wires, and I'll show you the one that is not broken. Here's the one that is not broken, and you can see it has two little wires. And it consists of 3 special diodes that are all in series inside this one package. Now, why are they special? They're special because they maintain a very consistent voltage drop over a wide range of voltage and current flowing through them. Okay, very little difference. They do, however, change their forward voltage drop with temperature. But again, they do so in an extremely linear and predictable way. What is the advantage of that? Well, transistors, as they change in temperature, the VBE, or the voltage drop between base and emitter, will also change. When that changes, that tiny little bit of change there's only normally about maybe a 0.6 volt, 600 millivolts, 650 millivolts, 700 millivolt drop, somewhere around there. And as that changes, the current, the forward current from base to emitter, is a direct influence over the current flow from emitter, from collector to emitter, okay? And so that VBE will change as the transistor heats up, which means this current will change even though you're not applying any signal to the base. So the whole bias will drift out of whack. So when you first turn your amplifier on, it might be right in bias, but then as you play the amplifier for a while and it heats up, the bias will actually drift out of range. Well, these diodes are right back here in your bias set circuit. So there's the pot that adjusts the bias, and if you follow the wire, it goes through these diodes and up to the other transistor here. This is called your bias spreader circuit. By adjusting this resistance, you're changing the voltage between here and here, which is changing the voltage that biases these. Once you get that set properly, since this is sitting on the heatsink with the transistor, as the transistors heat up, this heats up with it. As the VBE changes on these, the voltage drop changes on these. It then feeds back through here, which will adjust the voltage here automatically, which will bring this bias back into range. So it's kind of an automatic bias setting circuit. And that's what this is for. So these have to be properly coupled to your output transistors on the same heatsink. And they have to be very consistent in the forward voltage drop with respect to the voltage and current flowing through them. And they have to change in a very predictable manner with temperature. So that's what this is. Now, why am I going through all this detail? Well, these are it's pretty common to see this. The wires on these are very, very thin. They're single-stranded, and they break off very easily because of how they're put in there. And what happens is these break off, and you can't get them anymore. These are hard to find. You can see the little horseshoe on them? That's where your mounting screw goes. This will mount right on the back of the heatsink here, right alongside your transistor. And it'll couple thermally to that transistor. Now, a lot of times when these fail, there's a lot of things floating around on the internet where they'll say just take a 3 1N4148 diodes and put them in series or something like that. Well, they will give you a similar voltage drop, but 1N4148s and other similar diodes to those, you'll find out when you put different forward current through them, that VBE will change. Whereas on these types of diodes, they will not. Now, there are diodes like the UF1004 that have a very similar thermal and so forth tracking to this, but they're huge. So for instance, if you took 3 of those and put them in series and glued them to a little ring like this is a homemade one, you could see it's pretty big and bulky, but it works. And it's kind of messy, but it will work. And you can see my 3 little diodes in there, all soldered in series. But I've come up with, I think, a little bit more elegant design, and that's what we're going to look at. We are going to replace this, I'll put it here, with one of these. Can you see it? It's very tiny. Chances are I'm going to drop this and it's going to go flying across the room and we're never going to see it again. This is a stabistor, and it has very similar, it has a little higher voltage drop than these STVs do, but it tracks very similar to these and it will work in place of these. You might just have to make a little mod to the circuit, which I've done already. And if you notice, there's 6 pins on there. I don't know if you can see that as I bang the camera. I don't know if you can see that or not. But those 6 pins, let me put this back. Hold on. Here's the data sheet. It's called a CMX STB 400. And there's 3 versions, the 200, 300, and 400. We'll get into what that means in a minute. But you can see some of the characteristics. And if we go to the next page of the data sheet and see how these are wired, here's the STB 200, 300, and 400. The 200 has 2 diodes, the 300 has 3 diodes, 400 has 4 diodes. But each diode in each one of these, they're all identical. So you can buy this one and just wire it up. You can see how the pins are configured. Wire it up to turn it into either a 3 or a 4 diode system, depending on what wires you use. So if you go from pin 1 to 3, it's a 4 diode, so it would be like an STV 4H. And if you go from pins 1 to 2, it's like an STV 3H, which is what this is. Now, you might say, how am I going to hook wires up to that and put it on a heatsink? Well, that's where I decided to get a little bit creative. If you go online to eBay, you can buy these SOT23 adapter boards. Okay, so here's a pack of 10 of them. You break them apart, see? Just like that. They break apart. And you can solder the chip right onto that board, and then you have these nice little pins. And when you're done, you can make a little flange. And I'm going to put pictures up. I have photographs of this in the process of making it. And what you do is take a little bit of, I have some metal strap. And this is kind of a thick copper strap, and I just pounded it flat on my vise, on the anvil on the back of my vise, and then cut it. And I made a little, just a little loop, and then I used thermal glue, which is this stuff right here. And this is actually a thermally conductive. It works almost as good as regular thermal paste, but in glue form, so it hardens, and it's thermally conductive, but it is not electrically conductive. And that you got to be careful, because some of this thermal glue is electrically conductive. This is not. Okay, it's glue. It is not like heatsink paste. Heatsink paste stays like grease all the time. This cures just like glue cures. It gets hard. And it gets sticky, and it will fuse things together. That's its job. So what you do is you're going to solder the little chip to the board, put your leads on pins 1 and 2, if you have an STV3 like this. You're then going to put this face down onto your little metal flange, and then cut your little hole here for the mounting hole. And when you're done with a little bit of heat shrink and a little bit of neatness, you have a little device like this. And it's much, much more durable. And I used some of this heat-proof tubing on here. And you can see the glue in there. And when I made it, you could see the little black heat shrink on either side, so it insulates the little wires from touching the copper. But the actual face, the top face of the STB unit is actually physically contacting this metal. So let's see how it works. Okay, the meter is set to diode check, and we will connect it just like a diode. And you can see our forward voltage drop is about, let me put my microphone on here. Sorry. And you can see our forward voltage drop is about 1.81 volts. And if we get a little bit of chill spray, okay, so we just get some freeze spray, just shoot it onto the back of this. Watch how quick it changes. It's so nicely thermally coupled that basically As soon as I cool this metal flange, it goes straight through that glue and straight onto this. So it's very fast reacting, and that's what's good. A lot of these homemade ones with balls of epoxy glue and stuff that you see online, like with these, they don't really react as quickly as this. And if you take, for instance, the heat gun and just put a little bit of heat to it, you can see it starts dropping down. Same thing. Okay? And it just tracks back and forth like that. Very cool, huh? Cool it back down. And before you know it, back up to normal. And room temperature. So it's a pretty good solution. It is a little bit bigger than the STB unit, but it should fit on the back of that heatsink just right. And I kind of bent this kind of at an angle so that the edge of the heat shrink is below, so this makes good surface contact. I'll show you some, like again, I'll show you some pictures here as we're going along. So that takes care of that problem. Now if we measure the voltage drop on this one, it is a little bit different. We're at about 1.51. And on this one, you're going to be 1.81. So 1.83 on this one. So you're talking about a 300 millivolt difference. Okay. And they will both track together at that distance from one another based with temperature very, very accurately. But that does have a slight discrepancy. However, we should be able to adjust that out with the bias pot. And what I did was I gave that pot a little bit more range by increasing this from a 100 ohm pot to a 200 ohm pot. Now I don't think even that you would need to do that. I think at the 100 ohms it still would be able to adjust, but instead of a single turn 100 ohm pot, and that's what actually failed here and went open, I put a 200 ohm, I think this is a 15 turn pot. It's either a 10 or a 15. But you can see them in there, those blue pots. One of them is for the DC offset or DC balance. And this one up here is for the bias. And this one I kept the original 100 ohm setting. This one I set for, I changed to a 100 or a 200 ohm pot. So that should do it. And I think I pointed those out wrong. This is the bias pot, which is the 200 ohm. This one that's right next to the differential pair, the JFET input pair, it's the 100 ohm. And as you can see on the schematic, let's see, it is not a pair of transistors. These are JFETs. And they're thermally coupled inside this little metal can. And you can see even one of these had been replaced. And this was supposedly the good channel here. This channel was the one that fried. And I mean, the heat sinks were burned up. Everything was, the whole board had charcoal on it. Just had to be cleaned. And you can see some of it I did not get totally cleaned off. Some of these black stains. So it must have gone up in a pretty impressive way when it failed. And I put a new, I know I get a lot of questions. This is an Omron MY4 24 volt relay. It's not the best design in the world because I would prefer because they don't use the normally closed contacts, and I would prefer the normally closed to be tied to ground so that when the protect circuit goes into protect, it shorts out the speakers so that you don't have any excessive arcing on this, because these are not bifurcated contacts. But it is what it is. It's just the way it works. So a really heavy short where this thing has to activate you're going to draw an arc on those contacts. It's just the way it was designed. So let's put this mess together and see if it works. All right, we have everything back in place. We have our sockets mounted, and let me see if I can zoom you in a little closer to see them. So there we go. So you could see the top one here. So the sockets are mounted, and if we go down a little bit, it's kind of hard to see, but see the little red and black wire right here coming down, and that is going down into, I don't know if we could see it from the other side maybe. Yeah, you can see it good there. And if you look right there, and you could see right there where the little stabistor is just tagged in under the socket, both on, let me back up, on the two transistors here for the two channels, and they're just going down in there. And then on this side, the transistors are mounted as they would have been in the older model that this heatsink was borrowed from, I'm sure, when Sansui built these. So this will get some thermal paste on it, on each one of these contact surfaces, and then it fits and couples onto the internal heatsink. So you'll have the fins here and then on there. And the nice thing, like I said, I used sill pads because actually, believe it or not, the sill pads that I'm using here have a better thermal transfer rate than mica and grease, the coupling grease. And they have the benefit of they don't get all, you don't have to deal with the grease or anything. They don't dry out or anything like that. The only downside is you have to be careful what application you use these on, because they can tear easily if you have a kind of a rougher mounting surface or something. So again, in this case, they're going to be just fine. So I think we're to a point, looking at this amp now, that we're ready to power it up and try it out and see if it works. Okay, here goes nothing. We have the 2 meters connected to the positive and negative power supply rail, and I am heavily current limited with just, I believe, the 40-watt bulb, which is the one clear on the end here, and we'll focus on that where we turn this on. All right, powering on. That's a good sign because it got real bright and then dimmed way down. It's about half brightness. And looking at the power supplies, we have plus and minus 27.8 volts right on the money. So that's a good sign. All right, now we're going to go through the amplifier and just check a couple of points to see if if we're getting any kind of signal through these transistors on both channels. So let me get set up for that. I hope everything's visible here. We're going to look, first of all, we're going to look across this stabistor and see if we have our voltage drop across here, to see if our bias spreader is at least conducting voltage of some sort. So let's look at the first channel, and it should be, we were seeing that 1.8 to 1.9 volt drop when we tested it on diode check, if you recall. So we're looking across our new stabistor. That one's 1.988, and this one 1.983. Wow, both channels are pretty close. Okay, now let's look at the bases of TR601 and TR602 with respect to ground. So let me grab ground here. And here's the base, TR601. We have 539 millivolts. And of the 602, we have minus 658. So you could see it's out of balance. And then if we go to the other channel, minus 396 and 829 millivolts. So that just tells us that our bias and offset pots are not properly set. And that doesn't surprise me. And we're also running at very limited voltage. We should have somewhere in the line of 50 or 60 volts, and we're only at 27 volts plus and minus. But the good news is we are getting drive voltage out to the bases, or bias voltage. And it just means that those pots, if you remember, I replaced the bias and DC offset pots with multi-turn ones, and I roughly set them to where they were, but of course the one pot was open for the bias, so I couldn't measure where it was set, so I kind of just put it at the center of its travel. So we're going to have to adjust all that, but I think this is working. Let's go across the speaker terminals now, and let's see if we're getting any kind of DC offset, and I'm sure you'll get something. So, am I still in view? Yes, I believe I am. I didn't even check to see if the speakers were selected. So nothing there. Nothing there. Well, 27 millivolts. And what's on this one? About 50 millivolts. How about here? Are we just picking up garbage? I think we're picking up garbage here. Let's check and see if our speakers are selected. Yeah, speaker A. Yeah, the speakers were turned off. All right, now we have speaker A selected. Helps when you check those things ahead of time, doesn't it? All right. Let's see what we have now. And it's not reading anything for speaker A, which means the transistors are just not turned on right now. And we're not reading anything for speaker for the left channel. So it just tells me that these that the bias isn't up far enough for these to start conducting yet. So the output transistors aren't even doing anything yet. All right, let's try to increase our voltage a little bit and bring a little bit more. Okay, we're currently on a 40 watt current limiter. We're going to switch it over to a 100 watt. So let me flip this one off and this one on. And now we're up to about 30 volts. And I don't seem to see anything dropping there. But I do not see any, the light is still, it's dim, but it's still pretty bright for what it is. We're at about half of an amp, about 500 milliamps of idle current, and I did not hear the protect relays come in yet. And we only have about 73 volts going into the power supply. So let me go through and do a couple more tests and see if the transistors have turned on yet. Okay, some of you may have already realized this, but in the two clips ago, when I looked at the speaker terminals, what do you think the big problem is with that test when I did that? Did you give up? Well, at that reduced voltage, the protect circuit would not activate. If the protect relay didn't come on, then even with the speaker switch turned on, you know, the speaker A selected, you would still not get any continuity from the amplifier through the relay out to the speaker terminals. So that was a worthless test. If you want to check, you know, before the protect circuit comes in, you really have to check it directly at the junction of the emitter resistor. So you would have to go right here where these two 5 watt, you know, 0.33 ohm resistors come together on the board. So let's do that. And again, I'll turn it on. And now I have the 100-watt bulb in there. And if we go from, and this is going to show us our DC offset. And let me go down just a little bit so you can see the camera at the bottom of the screen. There, can you see that? I'm not liking this meter. I'll admit, see how noisy it is? It's just not a good meter, and it has a really bad burden voltage for the milliamps. I said, you know, when I first tried this out, I kind of liked how fast the ohms mode was and everything, but not a good meter. Not recommended at this point in time because it's got a lot of quirks about it. So let's get our other meter out, namely our Fluke 87. And I'm still using the 187 to measure one of the DC rails. And I think this will give us a little better results. I'll have to back you out a little bit. There. I'll plug this in. Okay. Okay, channel 1, our DC offset is about 55 millivolts. Go to millivolt range. Yep, 54.6. That's a little high. And this channel, it's really high. It's almost 200 millivolts. Okay, the phone rang. So we have DC offset on there, and so the transistors are turning on and conducting, and I can feel them. They're all four above room temperature now, so they are warming up a little bit. So they're definitely conducting. So let's see if we can go and do adjust the DC offset and the idle current. I'm still a little concerned about that 100-watt bulb. I'm not sure how hard that's supposed to idle, but I have 539 milliamps at 73 volts. And that bulb's pretty bright for that. I mean, it's not super bright. It's still only about half brightness. But I would expect when this thing's up and idling properly, I would be a lot lower current than that. But I don't know. We'll have to see. So let's see if this thing responds to any of our adjustments. All right, I am now connected across the emitter resistors of TR601 and 602 of the left channel. And what they want for idle current is 10 millivolts, plus or minus 1 millivolt. So that's what we're going to look at. And you can see, here's the, just to give you a rundown in case you don't know. So this side of the emitter resistors, this goes to the emitter of one transistor, one output transistor. This goes to the emitter of the other one. And then they both tie together there. And where these two tie together, that's your speaker output. That goes through this coil and the resistor that are in parallel and goes out to the speaker terminals. So if I back you back out here and I look down at the meter, what we should see is about 10 millivolts when we turn this on. I have no idea where it is, but being that I could feel them get above room temperature and start to warm up, I'm thinking there's more than 10 millivolts. So let's see what we get. That's just a little bit more than 10 millivolts. So that's idling really hot. So if we put full power to this amplifier right now, it would really start to cook. So that's not a big deal. That's probably because of the, where it's adjusted right now. The big thing is I want to see is, can we reduce it? Because remember, we're using our homemade thermistor or stabistor and a different potentiometer that has more adjustment in it, that goes to this 200 ohm instead of 100 ohm. So let me get this on here. Oh, look at that. Boy, it's adjusting really easily. Okay. So we're going to take it all the way down, and I just heard the protect relay come in. And let's bring it all the way down to 10 millivolts. And there's 10 millivolts roughly, a little bit under. Let's see here, turn it up a little bit. You have to let it settle, because as you adjust something that much, it's going to change. So we're going to leave that there at 10. Now let's take our meter and move it to the other channel. Same place. And it is equally as misaligned. So let's put that up in there. And good grief, it's actually working, huh? Sometimes even a blind squirrel finds an acorn, huh? All right, I'm just going to let this settle a little bit. It's going to drop. Because, you know, you make a big adjustment like that, those stabistors take some time to stabilize also from the heat. And so do the transistors, so it's going to settle. And it's 10 millivolts plus or minus 1 millivolt is the spec. And I have a feeling after this thing warms up for a while, we're going to have to realign it again. And you can see right now it's still dropping. So we'll touch it up a little bit. You know, when it was that far off. And I believe our protect relay is pulled in. Let me look here. Yes, it appears to be in, as far as I can see. Let's see if the relay, yep. That's another thing I like about this relay that I used. Let me zoom you in. Okay. This is a really cool relay because it has an indicator when it's pulled in. See how right now you have these little orange dots here and here? When I turn the amplifier off, the relay drops out and you can see that it turns black. Let's turn the amp back on. And see it turn yet orange, and that means the relay's pulled in. So I like these relays. And then look how dim our bulb is now. And our idle current is down to 433 milliamps. So everything is much closer to where I would expect it to be. All right, now we can now go into the speaker terminals and we can look for DC offset and adjust that. Okay, I have both meters connected so that I didn't have to keep switching the probes back and forth. And I had to go back and forth a couple more times because they would creep up and creep around a little bit as the amp warmed up. It's been on for about 10 minutes now, and it's settled in. And look at our dim bulb now. Yeah. And our idle current is 304 milliamps. And now we have 108 volts. So we can almost switch this over to full power. I'm still not going to let it off the leash yet. So these will need readjusted once we get full power to it. But I want to set the DC offset right now because we're pretty close with 108 volts mains going in. And we're going to look at the DC offset now. Okay, they tell you to look at the speaker terminals, but it's much easier to just connect to the other side of the emitter resistors with respect to ground. because the other side of the emitter resistors is where, if you look here, it's where those two resistors converge, and that goes straight out to your speaker terminals. So that's a good place, and just connect to a ground lug. And looking at our DC offset, this channel's not horrible. It's at 10 millivolts. This one is 134, so it's off a good bit. So we're going to adjust both channels there. Let's start with the one that has the worst offset. And we'll see if we can bring it into range. Okay, that's the wrong way. All right, it's adjusting. This is good. That means both transistors are doing their thing. Okay. And of course, this is going to go all over the place as it settles. It's just kind of the way it works. And this one here just needs a little touch. Okay. I think that's good. Now we will go back in after we did this, and we will once again check our bias one last time and make sure it's right at that 10 millivolts where they want it. And then we'll apply full power and adjust it one final time. Okay, I'd say those are holding pretty good there. Let me get this bottom one just a little bit and drop it down just a little. And then what's going to happen is we're going to go to full power now. And it'll creep up ever so slightly. And we expect that because now our mains voltage is now 120 volts where it belongs, with no current limiting whatsoever. You have to do this like this with this current limiting because it's very easy to overload a transistor and have this thing just melt down again and burn all the transistors. These amps are really delicate for that. Okay, and you can see it now creeped up, so we're going to bring it down to 10 millivolts again. Okay. That's pretty close. And we'll bring this up. And again, we talked about bias before. It's not super critical. You just want it to be low enough to keep the amp idling cool and high enough to prevent any type of crossover distortion. And that's really, and you get a pretty wide margin of error, even though some of the some of the books give you a real tight tolerance, but it's really not as bad as you might think. So we're just going to let it sit there and stabilize, and I think we'll be ready to pass a signal through it and see if we get some sound. Before we proceed to the next clip, I'm going to do this little video on my camera, on my phone, just because it's easier. But I kind of want to share something with you because I make a mistake in these next clips on what I'm calling transformer sag, which is from the isolation transformer. So if you look down here, these are the two breakers that control the mains, the unisolated mains for the bench, and the isolated supply that controls the dim bulb tester and all these other device under test things. And it goes to that great big transformer in the back, which is in this box. And if you notice, there's these two buttons. And when I turn this thing on, you can really hear, I don't know if you can hear that, but you can hear the hum of that big transformer. It's a 70 amp transformer. And on top, I have some very large ballast bulbs. And those are current limiting, and they're there for two different reasons. Number one, to provide kind of a fail-safe. There's basically 1,500 watts of bulb filaments up there, and because they're pretty large, you know, compared to a normal bulb. And what these buttons do here is they disable or bypass those bulbs up there. And in order to do that, you press this button and it pulls in a relay that bypasses it. And you can see if I push it, that light goes out, and that means you have full power. Now, why did I do that? Well, first of all, as a fail-safe, like I said. But second of all, this transformer is so huge that the inrush current, when I flip the breaker to turn it on, actually pops the breaker just as you turn it on. So there has to be a current limiting load when you first turn it on. So it's just kind of the way that I have this. And what sometimes happens is when I come downstairs to do something real quick to shoot a clip, because I don't do all this stuff straight through, I do it as I have time, I'll turn this on and sometimes I'll forget to hit the bypass switch. So that means that amplifier in the next test that we do is running through these bulbs. Now, even though they're very high wattage, they are providing some current limit, which is going to cause a little bit of sag in our mains voltage. So keep that in mind when we do this clip. So I was wrong when I said the transformer was causing the voltage drop. It was actually those bulbs up there causing the voltage drop because I forgot to hit the bypass switch. So just so you know that. All right, on with the video. Okay, we have the big oscilloscope going. We have all the noisy fans of everything that's running. If you look up here, we have the oscilloscope displayed on the monitor up here, so it's easier to see. Well, maybe with this light off it's easier to see. Okay, and we're going to turn the amplifier on, and we have a 1 kilohertz signal connected to the input, and we have our 8 ohm dummy load connected to the speaker terminals, and we're reading across the speaker terminals. And if I give you a little better view there, you can see all the information on the right hand side. The orange and the purple displays are the actual wattage of the two channels, and the yellow and blue displays tell you the RMS voltage, and we can see the actual waveform. And really, I'm concerned about, I don't have the extra heatsink connected, so this is still not on there. So we have limited heatsink, and I want that on purpose. I'm going to, if this works, we're going to run this thing and warm it up and make sure that our bias tracking works, that those new Stabistor units that we built work. Okay, let's start out. 1 kilohertz signal. It works. Nice. Okay, there's about 25 watts per channel, 24 watts, something like that. And it's cruising along quite well. Nice looking sine wave. Now, of course, there's a couple things you have to take note. I'm just going to talk to you while we monitor this. We're kind of running it at about 1/4 of its power. And I'm still connected to the isolation transformer and that whole side over there for the mains. And even though that is a massive transformer I have for my isolation transformer, it's good for up to 70 amps. You're still going to get a little bit of transformer sag under heavy load. So it wouldn't surprise me if we do get a little bit of, at low frequency or at very high power, if we get a little bit of sag on our power supply, because you have an isolation transformer driving the power transformer. So, and these Sansui amps only have a 10,000 microfarad filter capacitors at on the main power rails. So you know, you're going to get that. So this is not really a good total all-out performance evaluation. We're just checking to see if everything works. And you'll see probably what I think you're going to see is it's going to have a hard time with a square wave, but until we get everything out, you know, on a solid power line. Let's run this up now and see. And let's see if it, right there, we're starting to get into right around 87 watts. I'm starting to hit the rails. See it? And it is clipping very, very good. I mean, it's clipping symmetrically. So right there's about 78 watts per channel. I bet we are just smoking those heat sinks right now. Okay, so let's turn that down a little bit and let's feel our heat sink. That's warm. It's not burning hot, but it is warm. I mean, like above room temperature warm. But I mean, you can hold your hand on it all day long. I mean, it's just actually nice and warm. Let's see what the temperature is on it. And it is about 120 degrees Fahrenheit, which is about 49 degrees Celsius, 50 degrees C. Not bad. And it's still idling right along. I'm going to crank the power up again. You can kind of see down in the left side of the screen there, you can see the scope. We're going to go up. I'm going to run this at about, I'm running at 57 watts per channel right now. I just want to heat up that heat sink a good bit. I want to get to about maybe around 60 degrees C or so, maybe. Let me see here. Yeah, the devices themselves are not very hot. Nope, it's just not getting super hot. I mean, it's getting warmer, but it's not uncomfortable to hold my hand on it quite yet. Now I feel it. Now it's starting to heat up a little bit. That's better. 58C. Okay. We're now going to, while we're talking, we're going to go down here, and you can see with signal on it, that is the millivolts on your bias circuit. I want to see, this should drop down back down to somewhere around our 10 millivolts if our bias spreader circuit is working properly. And it's going to take it a little time, but you can see we're already down to 18 millivolts, 17, 16, so it's going to bring it right back down anywhere. It probably will be a little above 10 because this thing's really hot right now. But you can see the bias is staying really, really nice and solid. And that's what those stabistors are supposed to do. Within a minute or so, this should be all nice and settled in again, and it already is. Look, 13 millivolts. Beautiful. So our bias is good. What you don't want is what you call bias creep, and that is what I refer to when you heat the amplifier up and then you turn the volume back down, and this doesn't happen. It just stays up real high until the amp actually cools down physically. But you can see this heatsink is hot right now. It is really hot. And it's holding bias right at 12 millivolts. That's perfect. That's beautiful. I would have to say this amplifier is fixed, and the extensive amount of work that I did on it first try was successful, and that's pretty rare, huh? But, well, I think we're ready to kind of start buttoning this up a little bit, and we'll do some real-world testing on it just to see if these main filter capacitors here on the DC rails are are good if they're solid, or if they sag, if the power supply sags with a strong mains line, we may want to change these out too. I usually don't like to replace these because they usually are in good condition on these amps, and this is a more expensive part to replace if we have to do it. So I don't know, everything looks good. Of course, we didn't do square wave, we didn't do frequency sweep, we didn't do frequency analysis, we didn't do any of that. Didn't check for harmonic distortion, but we'll do all that next. All right, we stuck a little bit of thermal compound on this thing, and we're now ready to couple it up to the other half of the heatsink and get the screws in, and we'll be right back. Okay, we're put together now, and I have the amplifier connected to just a normal mains connection instead of through the isolation transformer. So we're kind of eliminating that isolation transformer sag that we're talking about. See how this thing performs, and if maybe we got some problems with our capacitors. So amp has been turned on for a few minutes. I haven't put any signal to it yet. Just wanted to kind of get it to stabilize. Okay, signal generator on, 1 kilohertz sine wave. And let's see, remember we were getting, it was starting to clip out somewhere around 85 watts, was it? Have to go back and look, but let's see what we get now. All right, there it's starting to clip, and look at that, 129 watts per channel, and it's sitting at 118 to 120, about 120 watts. Not bad for a 90 watt amp. And I'd say those capacitors are just fine, so we're not going to have to touch those. I did not do a recap on this thing other than the power amp and the power supply board, and I don't think we're going to need to. We're going to test it. If it needs it, we will. If it doesn't, we're going to leave it alone. Okay, I know this video is getting a little bit long now, and it's going to take me some time to edit, so I'm going to end this here. We know the amplifier works, and it's working well. We'll do our testing and evaluation on the last part. So I'll just do that in a separate video, and that'll end this series on this. So we're just going to have 2 videos for this thing. But until then, as always, I wish you all peace, joy, happiness, and good health in your lives. And I'll get this posted up there, and then we will do the actual testing and evaluation of how it performs in the last video. Take care and stay well, and we'll see you again real soon. Bye-bye.